All right, getting back to section 11.5. Now we're going to look at some applications that involve fluency with these equations that we learned about in the last video. So to start off with, let's talk about what happens when two planes intersect. When two planes intersect, the intersection forms a line. So you remember all the graphs that you learn in two dimension and the XY plane, when they intersect, it always intersects at one point, or maybe even multiple points. Right here, though, when we have two planes that intersect, right, it forms a line. Using that, or using what we know, we can actually find the angle between the planes using a dot product, right? So remember, your dot products are a way for you to relate the magnitude of two vectors with the yeah, with the angle that's between the two vectors. And in the last video, we learned that with planes, we have something called the normal vector that is kind of a characteristic of that plane. And other note here is that we can use the cross products of the normal vectors to determine the equation of that line of intersection. So I'm going to illustrate this real quick with a sheet of paper. There we go. So got a sheet of paper here, right? The sheet of paper represents a plane. Okay. Let's say instead that I fold this into two. I don't even have to be same. So let's say that I have these two planes, right? So this side of the paper is one plane, this side of the paper is another plane. Notice where those two planes intersect, what do we have? We have a line, straight line, an edge, right? If I want to find the angle between these two, right? One option might be, oh, I can just find two vectors that are in this plane that intersect here. But the thing is that won't necessarily give you what you want. It's too general because, I mean, even if they intersect at one point here, you might have one vector going this way and the other vector going like that. Yeah. And that poses too many problems. So instead, what we do is we look at the normal vectors. So the idea is if I have two normal vectors, yeah, there we go. All right, I have two vectors that are at a 90-degree angle with these planes. Okay, so we can agree these are 90 degrees to the sheets of paper that they're sticking out of. Notice where those two vectors intersect, they're going to make the same angle that the sheet of paper does, right? Because this event essentially is going to form some kind of a rhombus. Pretty cool. Other thing to note is that when we take the cross product of these two vectors, this is, yeah. When we take the cross product of these two vectors, remember how the cross product works with our right-hand rule, right? I can sweep this vector into this vector, and the result is going to be pointing back at me. If these were situated in the paper, we would find that that cross product is actually parallel to the line that forms between the two planes. So that's kind of a visual representation of why this works out the way it does. And let's look at an example. So for this example, we want to find the angle between the two planes given here. Then we want to find parametric equations of their line of intersection. There we go. Okay, so first off, if I want to find the angle between the two planes, I need to be able to figure out what the normal vectors are. Well, this is where that comment I made in the last video comes back, right? Knowing that this is the general form for a plane allows us to say, okay, this is the general form. I know that the normal vector is just the coefficients for x, y, and z. So if I call this one line 1, and I call this one line 2, right? We know that the normal vector for line 1 is given by 1, -2, 1. And I know that the normal vector, why did I write line? That's a plane. Superman. All right, but anyway, the normal vector for plane number 2 is given to us by 2, 3, -2. So we have our normal vectors. Now we can get the angle between these two using the dot product. And we can figure out the equation, the parametric equations of the line by taking the cross product. All right, so dot product. I know that n1 dot n2 is equal to the magnitude of n1 times the magnitude of n2 times cosine of the angle between them. So to remind you, the magnitude we can get using our extended Pythagorean theorem. So 1 squared plus -2 squared plus 1 squared. For n1, I get a magnitude of square root 6. For n2, if I use the similar formula, right, that's 2 squared 4 plus 3 squared 9 gives me 13. Add -2 squared 4, you get the square root of 17. And so now we know the magnitudes. Remember, if we have component forms for these vectors, we can find our dot product by just multiplying and adding. So remember, dot product, we have 1 times 2 plus -2 times 3 plus 1 times -2. So that'll be 2 minus 6 minus 2. So -6. And then when I multiply the square roots together, remember this is the same as if I multiplied the insides. Okay. So solving for theta, I know I'm going to have to divide by this coefficient first, and then I have to undo cosine, which means I use arc cosine. So I know that this angle will be arc cosine of -6 over the square root of 17 times 6. And that would be the angle. Remember, on a scientific calculator, you can actually get the radian measure for this angle. Okay, now the next thing is to find the equations that describe the line of intersection. So we're going to start with our cross product, n1 cross n2. So we have I, we have J, we have K. Then we have N1 and N2. All right, if I decompose this one, we get I times this determinant. Oh, oops, not that one. Minus J times this determinant plus k times this determinant. So I end up getting 4 minus 3. So that's just 1i. -2 minus 2. So -4. Since there's already a minus there, it'll be plus 4j. 3 minus -4 gives me plus 7k. So that means that the slopes that I'm going to use in my parametric equations are going to be 1 for the x equation, 4 for the y equation, and 7 for the z equation. Now, the other thing is that to write the equation for this line, I also need to know a point that's on the line. So basically, I need to know a value of x, y, and z that's going to satisfy both of these equations. With this one, because there's no constant at the end, that's trivial, right? If I plug 0 in for x, y, and z, then both equations will be correct, right? Because I get 0 equals 0 and 0 equals 0. So, didn't give myself enough space here. These are planes from earlier. There we go. So to write my parametric equations, right, we're using the point 0, 0, 0, and we're using direction vector 1, 4, 7. So for x, my parametric equation will be 0 plus 1t, or just t. For y, 0 plus 4t, or just 4t. Z, 0 plus 7t, or just 7t. And these are the parametric equations that describe the line of intersection. All right. And then the last type of application that we'll look at today has to do with finding the distance between various three-dimensional entities that don't cross. So for example, we could use this to find the distance between a point and a plane that don't intersect, right? So it'd be like a plane and then a point that's somewhere above or below it. We could also use it to find the distance between points and lines, or two parallel planes, or two parallel lines, or even a line that's parallel to a plane, right? So all of this kind of goes back to some of the other ideas that we've learned. When it comes to finding the distance between a point and a plane, we would use projection. So to illustrate this, bring our plane back here. Yeah. So to illustrate this idea, if I have a plane in 3 dimensions, so here's a plane. Let's say that I have a point that we are going to call Q that's hovering above this plane. I can actually find the distance, and by distance I mean the shortest distance between Q and a point on the plane P, specifically the point that's directly underneath or closest to the point Q. And I don't need to necessarily know what that point is to do it. I could actually use any point that I know is on the plane P, right? So that could be any point that satisfies the equation of the plane, right? And we can do this using projections. So if I call this point, random point on the plane, any point, if I call it P, then I can make a vector that goes from that point P up to the point Q. So this would be our vector PQ. And if I look at my normal vector, right, that's essentially this, yeah, it's essentially a vector that looks kind of like this dashed line that I've drawn here, right? So this is also our normal vector. And it doesn't matter if the normal vector passes through Q either, right? Because if I make my projection, right, then this distance that I find is going to be the same no matter what. And remember, n really is just here for us to figure out a distance or a direction, right? Because remember, your shortest distance is going to be the one that is perpendicular to the plane that you're coming out of. So anyway, remember how projections work. Basically, you take a vector and you smush it down onto the direction vector, right? This distance, so remember, n can go past there, n can go so that it doesn't even get to q. It doesn't really matter, right? It just has to be perpendicular to the plane, which by definition n is, right? But whatever we get from doing the projection, remember, gives us this vector, right? So the projection would give us the vector that goes directly from this point, whose coordinates we don't really know, up to the point Q. If I take the magnitude of this vector, of that projection, then I'm going to get the distance that is the shortest distance from this point to Q, which is what we're trying to find. Shortest distance from Q to the plane. All right, and reminding you of how projections work, right? PQ dot the direction, right? So that's the normal vector, divided by the magnitude of the direction. And the fact that we're dividing by this magnitude is why the length of n doesn't actually matter. Whenever we look at points that are, yeah, whenever we look at distance between a point and a line, though, it's a little bit different. So we can't really use that whole projection idea for points and lines, but we can use something similar. So like if I have a line and I have a point, again, we'll call that Q. I could pick any point on the line P or on the line, and we can call it P. And remember, the distance from the point to the line is specifically asking you for this one, right? That's the distance that's normal to that plane. Since we don't know the coordinates of that point, we can't really write a vector that goes from here to here. Otherwise, I mean, we could just use dot product and find what's orthogonal to it, right? But that's not really the case here. So if P is just the point whose coordinates we do know, I can again draw a vector that goes from P to Q, and we can call that PQ. Now remember, if I take the cross product of this and if I take the cross product of this and the direction vector of the line, remember, direction vector can be any vector that's along or parallel to this line. The length of it doesn't matter, all right? So it doesn't have to actually go to that point. It can go anywhere. It can go past it. It can go short of it. Doesn't matter. If I take the cross product of these two vectors, remember, what do I get? I get the normal vector, right? So if I cross PQ with this vector U, that gives me the direction of the line, I get a cross product. Basically, I get a vector that is coming directly out of the page, perpendicular to the page. And if I take the magnitude of that cross product and then I divide it by the magnitude of this vector u, then I end up getting this same distance here. So we can use this formula to find the distance between a line and a point. We can use the first one to find the distance between a plane and a point. And for other combinations, just remember, if I want to find the distance between two planes, I can always just pick a point on the top plane and find its distance from the bottom plane. Or if I have two parallel lines, I can do the same thing. Pick a point on one of the lines and then use this formula from the other line. So first example, find the distance between the point Q with the coordinates 1, 5, -4 and the plane 3x minus y plus 2z equals 6. So we're going to need to, so we're finding the distance between a point and a plane, meaning we're going to use this formula. All right, first thing is that I have to figure out a point P because I can't come up with PQ unless I know what P is. For that, I'm just going to figure out easiest possible way to make this equation true. So I need to choose a value for x, y, and z that will make this whole thing add up to 6. And I see here we're multiplying 2 times z. If I let z be 3 and everything else be 0, then the equation is true. So I know that a point on this plane would be 0, 0, 3. Alternatively, you could have x be 2 and everything else be 0. Or you could have y be -6 and everything else be 0. All of those would be points on this plane because all of those combinations would make the equation true. So we have our point P, which means that we can get our vector PQ by using P as the initial point and Q as the final point. So 1 minus 0, we get 1. 5 minus 0, we get 5. -4 minus 3, we get -7. It should be pointy. There we go. So that's our vector PQ. Next thing we need is to figure out the normal vector to this plane. Lucky for us, we know all about standard form and general form for equation of a plane. All I'd have to do is subtract the 6 from both sides, and it would be in general form. Since we don't actually rely on the constant at all, I can just pull the normal vector from these coefficients. So I know that the normal vector is given by 3, -1, 2. So now I have PQ, I have N. I can carry this formula out fairly easily. So I'm going to start by getting my dot product. PQ dot N. And remember, we're going to take the absolute value of that, which would make it so that it doesn't actually matter if P is initial or Q is initial. All right. So remember, all we have to do is take component times component. So 1 times 3, we get 3 plus 5 times -1, so -5, plus -7 times 2, that's -14. If I add those together, I get -16. Since we're taking the absolute value of that, we get 16. All right, and then the other part of the formula is finding the magnitude of the normal vector. And again, we just do extended Pythagorean theorem for that. So square root of 3 squared plus -1 squared plus 2 squared. All right, and combining those, I'm going to get the square root of 14. And we can't reduce that because that's 7 times 2. Okay, so now to answer my question, the distance between this point and this plane is going to be absolute value of my dot product, 16, divided by the magnitude of the normal vector, square root 14. And with a little quick math, that's going to be a little bit more than 4 point something. All right, moving on to another example. All right, we want to find the distance between two parallel planes. All right, so as I mentioned before, all we have to do here is pick a point that's on one of these planes and then do what we did in that last example, just using the point we picked and the plane that we didn't. Okay. So since I already kind of looked at this equation in the last example, why don't we use the point Q equal to 2, 0, 0? Yep. If I plug 2 in for x and 0 for everything else, I get 6 minus 6, which gives me 0. So we're going to let that be our point Q. Remember, we do need to know a point on this plane for us to be able to find PQ. So we can pick, let's see, immediately I'd say let's let y be equal to 2 and everything else be 0. All right, so now we have our 2 points. We can figure out PQ again by just using P as the initial, Q as the final. So 2 minus 0, I get 2. 0 minus 2, I get negative 2. And 0 minus 0, we get 0. So this is our vector PQ. Now we need to know the normal vector for the plane that we didn't use for Q. So we use this one for Q, we can't use that. So we'll use the second plane here to get our normal vector. So normal vector, again, we can just pull off these coefficients, 6, negative 2, 4. Remember, we don't use the constant for anything when we're getting the normal vector. So now that I have PQ and I have N, I can go back to the method that we did last time. I have to figure out the absolute value of the dot product between PQ and N. And I need to figure out the magnitude of N. So dot product, we've got 6 times 2, 12, plus negative 2 times negative 2, 4, plus 0 times 4, 0. So the dot product is going to be 16. Kind of funny that it worked out that way. And then for the magnitude of N, remember we're using our extended Pythagorean theorem. So that's going to give me 36 plus 4 gives me 40 plus 16 gives me 56. So I get the square root of 56 as the magnitude. And we could, all right, we could write this as 2 square root 14, right? Because that's 7 times 2 cubed. So if I take one of those 2's out, that's going to leave one of those 2's behind. So we could also write like that. And if I were to find the distance between that point that we got and this plane, we would have distance is equal to absolute value of our dot product, 16, divided by the magnitude of the normal vector, 2 square root 14. 16 over 2 reduces, so we could write this as 8 over the square root of 14. And again, on a scientific calculator, you wouldn't actually have to reduce it like this. You could type 16 over square root 56 in and get a decimal value. All right, last example. We want to find the distance between point Q and a line given by these parametric equations. So a reminder, because we're finding the distance between a point and a line, we're not using that same formula that we did for the other two examples. Instead, we're going to use our formula. Distance is equal to the magnitude of the cross product of PQ and the direction vector divided by the magnitude of the direction vector. So for this, we need to know two things. We need to know PQ, the vector. We need to know the direction vector U. Well, from the parametric equations, remember, how do we get the parametric equations, right? The constants, the intercepts in each of these represent the coordinate of a point that is on that line. That's going to be helpful because that gives us P. So we know that P is going to be -2, 0, 1. Right? And the slopes of each of these are obtained from, you guessed it, the direction vector. So our direction vector U is just 3, -2, 4. So now we have all of the things that we need to be able to carry out this computation. Well, almost. So we have P. Now we can get PQ just in a similar way that we did before. All right, so we can use P as the initial, Q as the terminal. So we get 3 minus -2, 5, -1 minus 0, -1, and 4 minus 1, 3. So we have our vector PQ and we have our vector U. Now, the numerator of this is going to rely on us finding the cross product between PQ and U. So we're going to set it up. PQ cross U is the determinant of this matrix. So PQ goes in your second row, and U goes in the third row. So we'll get I times the absolute value, or the determinant of this matrix, minus J times the determinant of 5, 3, 3, 4, plus K times the determinant of 5, 3, -1, -2. Writing that out, we get -4 minus -6, that's positive 2i. 20 minus 9, so minus 11j. -10 minus -3, so minus 7k. So this is my cross product, PQ cross U. The numerator of my distance equation here is the magnitude of this cross product. So we can do square root of 2 squared plus -11 squared plus -7 squared. So we get 4 plus 121 gives me 125. Plus 49 gives me 174. So I have the square root of 174. Now for the direction vector, magnitude for that one, it's just the square root of 3 squared plus -2 squared plus 4 squared, right? From those components. So that's going to be 9 and 4 make 13, and 16 makes the square root of 29. So the distance then is going to be the square root of 174 divided by the square root of 29. Remember with square roots, if you have a square root over a square root, you can just make it the square root of a fraction, right? So you can write your answer like that. Again, if you're using a scientific calculator and you're asked for a decimal value, you can just type in either of these and you'll get the answer, right? But that's the distance. And those are our examples. So to kind of recap that, we started off by figuring out the distance between various things. And well, we started out with intersections of planes. Remember, when two planes intersect, they form a line, right? The intersection is a line, not a point. We can find the angle between the two planes by using the dot product. We can also find the dot product of the normal vectors. Remember, it made that little rhombus shape when we looked at the paper and the pencils. Yeah. We can find the equation of the line by looking at the cross product of those normal vectors. Because remember, the cross product gives you a vector that's parallel to the line of intersection. So you can get a point on the line by just looking at the equation and figuring out what is the easiest thing I can plug in to make the equation true. And using the cross product to get the slopes of the parametric equations. Other than that, we looked at the distance between any two entities in the three-dimensional space. Remember, to find the distance between a point and a plane, use the projection, right? So basically the projection of PQ, which connects any point on the plane to the point in question, onto the vector that's normal to the plane. Right. And in a similar way, we could use the magnitude of the cross product to find the distance between a point and a line. And we could extend that to find distances between lines and lines that are parallel or planes and planes that are parallel. And yeah, that's it. Happy mathing.